Hello everyone and welcome to this demonstration on voice-enabled mobile clinical prescribing systems for 5G networks. The presentation has been prepared by Sumit Soman, Priyesh Ranjan and Praveen Srivastav from the Health Informatics Group at the Center for Development of Advanced Computing, C-DAC, Noida. We begin with a brief introduction of the topic. The healthcare domain has been an area of national significance, particularly in view of the recent pandemic outbreak. In these times, there is a critical need for healthcare services provided by clinicians and hospitals to be available to citizens across the country. This requires the development of scalable solutions that are delivered in a seamless manner to the end users. With the emergence of 5G technologies, there is promising potential in being able to deliver such solutions that would ensure streamlining of healthcare service delivery. This demonstration intends to present a voice-enabled clinical prescribing system that can be used by clinicians. It is part of a comprehensive mobile-based teleconsultation solution for patients, doctors, and healthcare workers. We present the solution developed and discuss the workflows for 5G enablement. We elucidate the problem areas and propose solution overview here. As hospitals have high patient loads, it is difficult for doctors to perform clinical data entry on hospital management information systems. Also, during pandemic outbreaks such as the current one due to COVID-19, patients are unable to visit hospitals for routine consultations. In order to address these problems, we developed a mobile-based telemedicine solution where patients can interact with doctors through audio-video calling and doctors can use a voice-based prescribing system to generate standard clinical terminology compliant medical prescriptions. We now present a brief demonstration of the application. The patient logs into the application using the mobile number, which is followed by OTP-based authentication. The user can raise a new request from the main menu. They select the hospital and the department and provide basic identifying details for patient registration, which also includes demographic information. They then select the medical symptoms that they may be facing, vitals such as height and weight, past medications that the patient may be taking, any previously diagnosed conditions of the patient, or allergies that the patient may be suffering from, and also provide a brief description of the problem being faced. Next, they proceed to select the slot at a suitable date for which they wish to take an appointment. Once this is done, they may additionally upload images or reports of infected sites for the doctor's reference. This is important as the patient may wish to upload large files or several images of past prescriptions or medical reports. Once this is done, a confirmation is shown. The patient can check the status of the booked appointment from the consultation and status menu. We now proceed to demonstrate the doctor's workflow. The doctor logs into the application using configured credentials for role-based access as per the hospital's policies. Once the doctor has logged in, he can view a dashboard showing statistics of teleconsultation requests and the list of requests can be viewed. The doctor can preview patient details and approve or reject a request, which sends a real-time notification to the patient. Once a request is approved, the doctor can enter the prescription page by selecting the list from the approved request list. The doctor can preview the images that were provided by the patient while submitting the request, as well as view other details that were submitted with the request. Here, the prescription components can be entered from the patient details or by using standardized clinical terminology, such as for diagnosis. In this example, the diagnosis is entered and a standard clinical terminology mapping is done. Various prescription components can be individually entered by the doctor, which can also be done using voice. Once the prescription components have been entered by the doctor, either using text or voice, the doctor can preview the prescription and make any changes that may be needed. Once he clicks on Save, the prescription preview is generated and changes can be made if required. The prescription can be saved and viewed from the list of completed requests. The patient is also notified of the completion of a request and the prescription can be viewed in the patient section of the app as well. This completes the workflow for the doctor. which also includes video calling the patient. The application has various productivity features shown here. The video calling is implemented using WebRTC with end-to-end encryption. The app uses push notifications for various workflows to indicate the status of requests to the patients. The clinical terminology compliant speech recognition engine improves productivity of clinicians as they can now input through voice instead of having to type the prescription components. The solution is also integrated with a web-based doctor desk for the convenience of doctors who can complete the workflow through web-based interfaces as well. We now present the workflow of the key components of our solution that would benefit by the 5G enablement. The first aspect is voice-enabled clinical prescribing system shown here. The doctor provides input using voice, which is converted to text using a cloud-based automatic speech recognition engine. The detected text is then mapped to standard clinical terminology through the hospital management system's terminology server. Once this is done, the standard text is mapped to clinical terminology and the list of strings are sent back to the front end for validation by the clinician. This process is time critical and hence a possible candidate for enabling as an ultra reliability low latency communication use case. As an example, we illustrate here the generation of the clinical terminology compliant voice based input for a sample prescription generation. When the network conditions are good, the speech to text detection is completed in a timely manner, which also includes the mapping to the clinical terminology as shown here. However, when the network conditions are poor, the detection of text from speech as well as the mapping to clinical terminology takes a longer time. It can be seen here that the time taken is longer and the packet error rate is also higher in this case. It can be seen that the speech recognition component of this solution is time critical and hence it's a possible candidate that can benefit by using 5G based URLLC use cases. The next workflow is the audio video calling option provided, which is done through a WebRTC server and can be initiated by the doctor from the mobile or web-based interfaces. The patient is provided with a real-time high-priority call-like notification on the mobile device to join the call initiated by the doctor. Once the patient joins the call, the doctor can perform the consultation and generate the prescription. The video calling infrastructure needs to be scalable for many users and high bandwidth services need to be provided for this. This can leverage the enhanced mobile broadband applications of 5G for scalability and reliability. Another use case of interest is document transfer, which can happen during patient request raise or doctor's prescription generation, as well as while viewing the documents. In this example, we emulate a scenario when a patient prescription is downloaded in poor and good network conditions. It can be seen here that when the network conditions are poor, the download or document transfer takes more time. On the other hand, when network conditions are good, the download is faster. We compare the network traffic and packet error rate in these two scenarios and the difference is evident. It can be noted here that real-time document sharing is a desirable feature, however it is limited by the present network capabilities and can benefit significantly by the network slicing primitives in 5G. This slide presents a possible deployment scenario for the developed solution with the various solution components, users, and indicative network infrastructure. The hospital premises largely house the server components of the solution, which include the application, database, WebRTC, and file transfer servers, and the ASR engine and the application and clinical terminology databases. The doctors can use web or mobile-based devices, while the patients largely use mobile equipment. As this is a work in progress, we conclude with a summary of workflows for 5G enablement in our voice-enabled clinical prescribing system. These include the ASR engine for clinical terminology compliant speech recognition, which is essential for generating standardized and interoperable patient electronic health records while also increasing the productivity of doctors. In addition, audio-video calling and real-time file transfer sharing also benefit from 5G use cases. This slide shows the details of the components used in our solution as an indicative reference. Finally, we thank the viewers for taking the time to view our presentation.
The liver attachments to the adrenal kidney were divided and the liver was reflected superiorly. The vena cava was identified. The main renal vein was identified. Coming superior to the main renal vein, staying right on the vena cava, all small vessels were clipped and then divided. Coming along with superior pole of the kidney, the tumor was dissected free from top of the kidney with clips and bovi. Coming along with superior pole of the kidney, the tumor was dissected free from the kidney with clips and bovi. The harmonic scalpel was utilized superiorly and laterally. Posterior attachments were divided between clips, and once the whole adrenal was mobilized, the adrenal vein and one large adrenal artery were noted. Were noted, doubly clipped and divided.